So, a very good morning to all of you. I cordially welcome you all for this important course, that is applied thermodynamics. So, the today's classroom discussion topic is the Rankine cycle performance improvement with the help of superheating and with the help of reheating parameters. So the same thing we have to discuss in the today's class. That is, how can we improve the Rankine cycle efficiency with the help of the superheating and with the help of the reheating. So the motivation of the today's class is it is very essential to know the working principle of a Rankine cycle with superheat and reheat, and you should represent the same on PV and TS diagrams to calculate the performance of a thermal power plant. And the outcome of the today's lecture is you should be able to represent Rankine cycle with superheating and Rankine cycle with reheating on PV and TS diagrams after listening this particular lecture. So now, what is the effect of the superheating, whether it is desirable or not? So here you can see the superheating of the steam increases the mean temperature of the heat addition. That is, what is the basic effect of the superheating means? It is increases the mean temperature of the heat addition. So similarly here, the superheating of the steam to a higher temperature is always desirable. So it is always desirable because the moisture content of the steam, which is leaving the turbine decreases as indicated by the state 2 dash. That is, in the next slide you are able to see what do you mean by the 2 dash. So that is there any limitations of the superheating? Yes. Always the metallurgical considerations are restricting the superheating temperature limits. That is, you cannot increase the superheating temperature like 3000 degrees centigrade or the 2500 degrees centigrade because there are no materials are available to withstand that particular the higher temperatures. So that is the meaning of the metallurgical considerations are basically imposing the limitation on the superheating temperature, but it is always desirable to have the superheated steam at the exit of the boiler which is entering into the turbine, because it is basically avoids erosion problems as well as the corrosion problems and the pitting of the blades. So these problems will be avoided whenever the exit of the boiler is a superheated steam and whenever it is entering into the steam turbine. So now this is the effect of the superheating. Now let us solve a problem on the superheating. So let us go through this particular problem. In a steam power plant operating on an ideal Rankine cycle, the steam enters the turbine at 3 megapascals and 400 degrees centigrade and it is exhausted to 10 kilopascals. So determine thermal efficiency. If the steam is superheated to so and so condition, also find out the thermal efficiency. Like this is asking the normal thermal efficiency. Second one, under the given conditions, what is the thermal efficiency? Third one is also same, under the given conditions, what is the thermal efficiency? So now here, so we are able to have the turbine inlet is 3 megapascal and 400 degrees centigrade. So it is a turbine inlet, it is the case A. So now the TS diagram here. So this is my 400 degrees centigrade. So it is my 400 degrees centigrade temperature line. It is a constant temperature. So it is a constant temperature is 400 degrees centigrade. And the initial condition is given as a 10 megapascals. So it is my constant pressure. It is a constant pressure line is passing like this. So it is a constant pressure. And here the temperature line is like this. So both are intersecting here each other. So it is a point number 1. So similarly now is isentropic expansion is a 1 to 2 because he has given the exhaust pressure value is equal to 10 kilopascals. So draw a 10 kilopascals line and wherever it is intersecting this vertical line. So this is my point number 2 dash. So it is my 1 dash. It is the initial condition is a 1 dash. So similarly you identify the remaining points, that is the 3 and 4 dash as well as the 1. So this is my initial condition is a 10 megapascal. So it is my 3 and 4 dash and 1. So that's why here 1, 2, 3, 4, 1 is basically representing 3 megapascals 400 degrees centigrade. Now he has also given the next condition as 500 degrees centigrade. So now the temperature value is increased from 400 degrees centigrade to is a 500 degrees centigrade, And similarly, the pressure value is also changed. That is, it is equivalent to is a 3 megapascals. So it is a 3 megapascals. So now the temperature is increased here. So it is the 500 degree centigrade temperature line. So it is represented by 1 double dash. So 1 double dash here and here it is a 2 double dash. So 1 double dash, 2 double dash, 3, 4 and 1 double dash, it is representing the second condition and it is the first condition. Next, the turbine inlet. So it is a 10 megapascal and 400 degrees centigrade. So it is the 10 megapascal sees here. So it is the 1 dash, 2 dash, 3, 4 and 1 dash. So these are the three different conditions are there for the different inlet and different inlet temperature conditions. So like this we are able to plot the TS diagram. Now after plotting the TS diagram, now from the steam tables, so always the steam tables are very important one. So at the state number 1, state number 2, state number 3 and the state number 4. So find out all the different property values and then find out what is the value of the exit condition. Whether the exit condition is wet or dry or superheated steam. So for this particular one, 122 is always isentropic expansion process. So S2 is equivalent to SF2 plus X into SFG2. So X2 value is lesser than 1. So that's why we are able to get exit is nothing but the wet steam. Wet steam is leaving this particular the boiler. So now substitute in the respective formulas of the H. So find out H and the WP, that is the work required to drive the pump. And similarly, what are the values of the heat supplied to the boiler? So that is 3036 is the heat supply and how much amount of the heat is rejected from the condenser. And you know what is the Rankine cycle plant efficiency. So for the simple condition for the A, that is the first condition, we find out the plant efficiency is equal to 34.11 percentage. Then for the second condition, so for the case B, so it is whenever it is 3 megapascal and 500 degree centigrade. Now this is a value we obtained for is a 3 megapascal and 400 degree centigrade. We got 34.11 percentage. Now the pressure remains constant as 3 megapascal, but the temperature is modified as 500 degree centigrade. So then the points on the Rankine cycle also will be modified like this. Now for this particular one, the property values will changes. So note down the property values, and here the X value we find it out as 0.878. So still it is the wet steam only because it is lesser than 1. So now in this particular case it is equal to 35.59 percentage. So here it is 34.11 and it is a 35.59. That is almost is a 1.5 percentage improvement is there. So whenever the steam is heated from 400 degrees centigrade to is a 500 degrees centigrade, that is for 100 degrees centigrade superheating, we are able to witness 1.5 percentage improvement in the thermal efficiency of the power plant. So similarly for the case C also, case C is the 10 megapascals as well as the 400 degrees centigrade. So for which also in a similar manner you find out. So here the X value is equal to once again 0.142. So it is the wet steam condition. So in this particular case we got highest percentage to the 38.66 percentage. So the increase in boiler pressure results in increase in the plant efficiency from 34.11 percentage to 38.66 percentage. That is in the first case we got 34.11 and in the second case we got 35.58 percentage. In the third case we got 38.66 percentage. That is in the first case we got 3 megapascal as well as the 400 degree centigrade. So that is the first condition. So in the third condition the boiler pressure is increased from 3 megapascals to 10 megapascals. Then the temperature will remain same. Then we are able to witness a drastic improvement in the overall plant efficiency, that is almost is a 4.5 percentage, almost 4.5 percentage improvement in the thermal efficiency of the power plant we are able to witness. So the next another important one is, so what are the advantages of the reheating of the steam, whether it is desirable or not. So that is very important one. So let us see first of all why we have to do reheating of the steam, whether it is desirable or not. So just you go through this particular important sentence. If the steam expands completely in a single stage, then the steam coming out of the turbine is very wet. So I told you that if the wet steam is leaving the boiler, when it is hitting the turbine blades, automatically erosion problems and corrosion problems and pitting of the turbine blades will occur. So due to which the turbine life will be reduces. So that's why, because the same thing, because it is basically resulting in erosion problem and the life of the turbine is also reduces. Now what we have to do now? So now it is done by allowing the steam to expand at intermediate pressure in a high pressure turbine and then taking out and sending back to the boiler where it is reheated at constant pressure until it reaches the inlet temperature of the first stage. So this process is known as reheating of the steam. So just once again I'm repeating. So what we have to do in the reheating means, so it is allowing the steam to expand to an intermediate pressure in a high pressure turbine. That is, we are using the two turbines here, high pressure turbine as well as the LP turbine, low pressure turbine, and then taking out and sending back to the boiler where it is reheated at constant pressure until it reaches the inlet temperature of the first stage. So that is known as the reheating. So what are the advantages of the reheating? So in the last sentence you are able to witness here, due to reheating, the work output of the turbine is basically increases and improving the thermal efficiency also. So that is always the reheating of the steam is desirable to increase the plant efficiency and to increase the turbine output. So whatever the theory so far we studied, the same thing we are able to witness by this particular schematic diagram here. So in the previous ideal Rankine cycle, we are using only one turbine, but in the reheat Rankine cycle, we are using the two types of the turbines. One is known as the HP turbine and the second one is known as the LP turbine. So here the superheated steam is entering into the HP turbine. Now it is once again, it is extracted from the HP turbine. Now it is sending back to the boiler. So in this particular the boiler, we are having the reheated tubes. So now this is at constant pressure, because the boiler constant pressure heating is taking place. At constant pressure, we are able to increase the temperature of this particular superheated steam. And once again, this particular superheated steam is sent back to LP turbine. So here, the point number 3, whatever the steam which is entering into the LP turbine, we are assuring that it is free from any type of the wet particles, so that the life of the turbine blades, the life of the turbine and similarly the turbine blades will not damage. So that we have to ensure whenever at point number 3 the superheated steam is entering into the LP turbine. The remaining one is exactly similar to the ideal Rankine cycle. So one side it is going to the condenser pump as well as the boiler. Only thing is that, so this particular extra one is basically added in the reheating factor. That is, the expansion of the steam is basically taking place in is a two stages, that is in the two turbines. That is, it is basically to avoid any wet particles are there in this particular the turbine which is hitting the basic LP turbine. So the same thing, how can we represent it on TS diagram as well as the HS diagram? Let us say that is the point number 1, it is basically the superheated state. So locate point number 1 in the superheated condition at the boiler pressure. So the P1 is the boiler pressure, it is the superheated condition point number 1. So 1 to 2. So 1 to 2 here we have taken it as the saturation line. So let us say it is the point number 2 is the saturation line. So now we are heating according to the constant pressure. So P2 is the reheating pressure. So in the reheater we are once again we are heating. So reheating. So point number 3. So it is a 2 to 3. The 3 is nothing but the LP turbine. So it's a constant temperature. So 2 to 3. So it is a point number 3. So 3 to 4. It is once again the LP turbine. 4 to 5 is the condenser. 5 to 6 is the pump. 6 to 1 is in the boiler. So like this we are able to represent the reheating of the steam in this particular the Rankine cycle, but you are able to see here 1 and 3 are basically at the same constant temperature values, but the pressure is basically different from point 1 to is a point 3, but point 1 and point 3 both are having the same temperature values. So here the reheating, that is amount of heat added during the reheating, that is the reheat is equal to H3 minus H2. Just you go through the previous diagram here. So how much amount of the heat is added? So that is H3 minus H2. So this is representing the reheating, that is H3 minus H2. So similarly, how much amount of the total heat supplied? That is, one thing is in the boiler and the second one is in the reheating. So just you go through here. So it is first one is the boiler, that is this is the boiler, H6 minus H1, it is the boiler, and next one is the H3 minus H2, it is in the reheater. So that is the total amount of the heat is supplied is given as a 12.20, and how much amount of the work is developed because it is the HP turbine and here it is the LP turbine. So just you go through here. So that is H1 minus H2, it is my HP turbine and this is my LP turbine 3 to 4. So the same thing we are able to represent, and pump work is always same, H6 minus H5, so that is equivalent to minus integration of V into dP. So W network is nothing but WT minus WP. So substitute here. So the efficiency of the reheating, that is the net work done by is the heat supplied. So we are able to find it as the reheating efficiency of the plant is basically find out with the help of the 12.23. So it is evident from the TS diagram that there is a very less gain in the thermal efficiency by reheating of the steam. That is improvement in the efficiency is there, but is very marginal. But only the quality of the exhaust steam is basically improved. That is important one. That is just you go through here, the quality of the exhaust steam. So here it is the point number 2, and the exhaust steam here it is the point number is a 4. So quality of the exhaust steam is basically improved. So however, the mean temperature of the heat addition can be increased by including the number of expansions and reheating processes. So that is the basic advantages of reheating. So how can we find out the reheating factor? So that is the reheating factor is nothing but actual enthalpy drop by isentropic enthalpy drop. That is, we are having number of stages. So in the previous expansion, we have taken only one stage, that is the one HP turbine and one LP turbine. So if you are taking the 2 stages and 3 stages, the expansion process is taking place, then how can you plot the HS diagram? So that is, this is entire thing is representing the isentropic drop. So this is representing isentropic, it is representing the isentropic drop. But due to the actual expansion means always there will be some losses and irreversibilities will be presented. So due to the presence of the irreversibilities, the isentropic expansion process is basically converted to the polytropic expansion process. So here it is the actual enthalpy drop and this is the isentropic enthalpy drop. So whenever you are having the actual as well as isentropic enthalpy drop, then how can we find out the stage efficiency? The stage efficiency is always equivalent to actual enthalpy drop by isentropic enthalpy drop. So actual is nothing but H1 minus H2 and isentropic is nothing but H1 minus H2S. So from this particular one, we are able to find out H2 value is equivalent to so and so. Once you know the stage efficiency, then you can find out H2 value. So like this, if there are more number of the stages are there, then the cumulative isentropic enthalpy drop is so and so. That is, it is the first stage, it is the second stage, and it is the third stage. So the reheat factor is basically defined as is a cumulative heat drop divided by the isentropic enthalpy drop. So cumulative heat drop by isentropic enthalpy drop. So just you go through here. So what is the isentropic enthalpy drop? The starting point is 1 and the final point is 5s. So the isentropic enthalpy drop is H1 minus H5s. The same thing is represented here. So H1 minus H5s, it is representing the total isentropic enthalpy drop, and here is a cumulative. The heat drops are represented here. The 12.28 is directly substituted here. So that is the reheat factor definition is very important one. That is a cumulative heat drop by the total isentropic heat drop. So that is the turbine efficiency is basically find out from the stage efficiency into the reheat factor. So now let us solve a problem based on this particular the reheat cycle. So just to go through the problem, he has given that it is operating on a theoretical reheat cycle. So write down the given data. So P1, P2, P3 are given as well as the T1, T3 are given. So locate the points on HS diagram. So point number 1, 150 bar. So find out the 150 bar. And similarly, the temperature is also given as the 550 degrees centigrade. So locate the point number 1. So then from point number 1, so draw a isentropic line. Draw an isentropic line. So this is my P2. So this is my P2. So this value is equivalent to 40 bar. So this value is equivalent to 40 bar. So from point number 1, draw a vertical line till it reaches the 40 bar line. So this is my point number 2. So from point number 2, it is reheating is taking place according to the constant pressure process till it attains 550 degrees centigrade. So it's the point number 3. So from the point number 3, isentropic expansion process is taking place till the pressure reaches point 1 bar. So draw a vertical line from the point number 3, and it is my point 1 bar line. So both are intersecting here. So locate the point number 4, and from the point number 4 is a constant pressure. So it is whenever it is reaching a saturated liquid line. Point number 5, 5 to 6 it is a pump, and 6 to 1 it is a boiler. So that is the representation of points on the Mollier diagram is very, very important. So once you identify 1 to 6 points, then you note down what are the corresponding enthalpy values and what are the corresponding entropy values and what is the exit dryness fraction of the steam from this particular the Mollier diagram. So that is from the Mollier diagram, just you find out all the values. Just now I told you here 1, 2, 3, 4, 5, 6. What are the values? Just you note down. And finally at the point number 4, what is the value? X is equivalent to 0.88, and is the first bit answer. Second bit answer, what is the pump work? Vf into P1 minus P3. So this is my pump work. So heat supplied will be, it is a boiler work plus is a reheater. So the total work is equivalent to so and so. It is the second bit answer. So the third bit is asking about the steam rate. So the formula is the 3600 by net work. So the net work can be found out from the thermal efficiency is equivalent to net work by heat supply. So that is the thermal efficiency of the cycle is equivalent to 43.8%, and the steam rate of the specific steam consumption is equivalent to 2.19 kgs per kilowatt hour. So now in the today's class we discussed about the important concepts of the improvement of the Rankine cycle efficiency with the help of the superheating as well as the reheating. Now let us see some of the important questions which are given on this concept in the GATE and IES examinations. The first question is, efficiency of the superheat Rankine cycle is higher than that of the simple Rankine cycle because why? The reheating cycle, or sorry, superheating Rankine cycle is giving you more efficiency as compared to the ordinary Rankine cycle efficiency. So the answer is B. That is, I told you that the mean temperature of the heat addition is basically higher for the superheat cycle as compared to the ideal Rankine cycle. The next question. A steam turbine operating with less moisture is dash. That is, the answer is more or less efficient, and dash less or more prone to the blade damage. So it is the GATE 1992 question. So I already explained the same concept. A steam turbine operating with less moisture is more efficient always. Always you should have the less moisture content. Otherwise we are able to have the pitting of the blades and erosion and corrosion of the blades, so that the turbine life will be reduces. So answer will be in the first fill in the blank. It is more efficient and less prone to the blade damage. So that is the second one is the less. The third question is the main advantage of a reheat Rankine cycle. So out of this A, B, C, D, so what is the right answer? That is, what is the main advantage of the reheat Rankine cycle? So the answer is reduced moisture content in the LP side of the turbine. That is the low pressure side of the turbine. We are able to have the reduced moisture content, because of which we are able to have the reheating concept. So this is a very, very important concept. So in this particular class, we discussed about what are the effects of the superheating and what are the effects of the reheating, and we solved a few problems on superheating and reheating. I hope this particular concept is very clear to all. So thank you one and all for listening this important lecture on superheating and reheating. Thank you.